So guys, welcome to Dr. Velocity channel. So today this is what we were doing. I know most of you did not manage to access Zoom, but you try to use Google Meet as well. So today we are looking at how you can express velocity as a function of position. So from what we did, we said that if you have a spring that is placed on this horizontal, so I don't know, my diagram is not well. If you have a spring, okay, let's say you stretch this spring to a certain displacement. Let me call this maximum displacement as the amplitude. You applied a certain force so that it can be stretched. So we were saying that you can express velocity as a function of position. So in this case, from what we did previously, we talked about the elastic potential energy, that it's the energy that a body possesses due to the applied force on that particular object. So if you have an object, you apply a force, it is going to be deformed. Then it will try to recover itself to its original position. So there will be a certain force that will try to restore that is a restoring force. Then there's also an applied force, where you apply force, then that same force is doing work on an object because the object is deforming. So how can you write the work done for that or the elastic potential energy for that particular object? We said that we derived that formula to say the elastic potential energy, which is PS, is given by 1/2 kx squared. So that is what we did. Then from today we are looking at how we can express this potential energy in terms of the velocity and also the amplitude. So in other words, we are trying to find the velocity from this same expression, which is the conservation of energy. So there are two energies that are taking place in this case. If you're dealing with a spring as a simple harmonic oscillator, when you apply a force on this spring will reach a certain displacement, and I'm calling this displacement as the maximum displacement, which is the amplitude, which is A. Then if you are to release this object, it will pass through an equilibrium position where you have x is equal to 0. Then it will continue to compress that spring, that displacement, which will be the negative A. Then we know to say at this equilibrium position where x is equal to 0, the only energy that we have there is the kinetic energy. That's where you have V max, velocity maximum, and since you have the maximum velocity, so that means you also have the maximum kinetic energy, because kinetic energy will depend on the velocity that an object is having. So basically what we have here, this formula is for the total mechanical energy, how you can find the total mechanical energy. So we know to say, let me try to erase. So if you're dealing with a spring, or a simple harmonic oscillator like a spring, the mechanical energy is just the kinetic energy plus the elastic potential energy. So this is what you should keep in mind. Then this elastic potential energy, we said it is nothing but 1 over 2 kx squared, where k is the spring constant. Then from this, we know to say our usual kinetic energy will always be 1 over 2 mv squared. So that is our kinetic energy. So how do you use these formulas if you are given a spring or any simple harmonic oscillator? So this is what we want to do. So at x is equal to 0, we have maximum velocity from what I've said. So since we have maximum velocity, that means our mechanical energy there is just the total kinetic energy, because at that point you have the maximum velocity. So then again, the other expression, the total mechanical energy is just 1 over 2 k a squared. At this point, this is where you have x is equal to a, where you have the maximum displacement. The maximum displacement is just the amplitude. So if you have, let me try maybe to show it on a diagram. So let's say you stretch this spring. So if this is an equilibrium position where x is equal to 0, then this is a maximum displacement. At this point, the only energy that you have at that point, if you have a maximum, if you have the maximum displacement, then that you only have the mechanical energy, which is Ka squared. So this energy that is you are having here, it can be equated to in short, this mechanical energy at that position, it is equal to the kinetic energy at that position if you are to release that same spring. If you release this spring to pass through this equilibrium position, at this equilibrium position, it is going to gain a maximum kinetic energy at that position. Then it is going to compress a spring with a certain maximum displacement, which is a negative amplitude. Then how can you find that velocity that is giving this spring a maximum kinetic energy? So this is what we're going to do. So what where this expression is coming from, it is from the conservation of energy, because the total kinetic energy plus the elastic potential energy should be equal to a constant, and that constant is what you call the mechanical energy. So we know this mechanical energy is just 1 over 2 k a squared. Then we can substitute. So we know to say maximum the kinetic energy is given by that, and also the elastic potential energy is k x squared, which is equal to which is equal to 1 over 2 k a squared. This a is giving us the total mechanical energy, because you have the maximum displacement, so that means that is what you're going to have. Then if you have x is equal to 0, then I said the only energy that you are going to have here it is this kinetic energy which is giving us the total mechanical energy. So if x, in this case x is equal to 0, then what we are going to have, our expression is going to be 1 over 2. Our expression is going to be 1 over 2 mv squared is equal to 1 over 2 ka squared. So from this you can also you can calculate the maximum velocity. So this expression can be used to calculate the maximum velocity. But if you are just trying to calculate a velocity at a certain position where x is greater than 0, then what we're going to get here is, this is what you're going to get. So here there was an error, should be a minus sign here, should be a minus sign. So this is what you're going to get in this case. So from that you can make v the subject of a formula, then your expression is going to look like this. So from that we have 1 over 2 ka squared minus 1 over 2 kx squared, which is equal to the kinetic energy. Then you can solve for v, because your interest is to find v at a certain position where x is not equal to 0, where x is greater than 0. So yeah, that's where it is coming from. Then from that we can solve some examples. So there are some examples that are here. So this is an example from college physics, or you call it theory. So we are given a 0.5 kg object connected to a light spring with a spring constant of 20.0 Newton meter, oscillate on a frictionless horizontal surface. Calculate the total energy of a system. So we are calculating the total energy, which is the mechanical energy, and the maximum speed of an object if the amplitude of motion is this. So in short, to have x is equal to a. So in this case we have the maximum displacement, which is 3.0 centimeter. Then if we have the maximum velocity or maximum speed, that means our x is equal to 0 in that case. So the only energy that is giving a mechanical energy, it is the kinetic energy. So in short, our expression is just like that. So you can equate these two guys, yeah, for finding the maximum velocity. But if you are finding if you want to find the mechanical energy, since you already have the maximum displacement, which is the amplitude, then 1 over 2 ka squared. So in this case we are given the maximum displacement, which is that. Then we also given the spring constant, which is 20.0. So from that you can try to solve. Make sure that you convert the displacement into its respective SI unit. So we are going to have 2, then you have 20 times 3.0 times 10 to the power negative 2, then you square that. So this is part of squaring there. So what are you going to get? So you're going to get your mechanical energy as 9.0 times 10 to the power negative 3 joules, if I'm not mistaken. So I'm not using a calculator, so you can verify that using a calculator. So that's your mechanical energy, your total energy that you're having. Then Then what about the maximum speed? So we just equate these two since we already have the mechanical energy. So we can equate kinetic energy to the mechanical energy. So what you're going to have here is kinetic energy being equal to mechanical energy. So 1/2 mv squared. This is V max. We are calling it a speed, which is 9.0 times 10 to the power negative 3 joules. So you can calculate for V in this case, because that is what you're finding. The mass is already given, which is 0.50 kg. Yeah, so that's how you solve for kinetic for maximum velocity. Then what about question B? What is the velocity of an object when it is when the displacement is 2.0? So if you have a displacement, then the formula we are going to use is E is equal to 1/2, because you have the kinetic energy, you have elastic potential energy, and also the mechanical energy. So since our interest is to find V, then you have mv squared. This is not V max because this is not the amplitude but just a displacement. Then you have 1/2 kx squared. We already have remember we already have our mechanical energy. It won't change. That is our total energy. So we are going to solve for V because our x is already given. Just substitute this into that. Yeah, the mass is given. Then solve for V because you're finding V. Then compute the kinetic and potential energy of the system when the displacement is 0. So in short, your potential energy, which is elastic, the same potential energy, which is kx squared, that is your potential energy. Then your kinetic energy is 1/2 mv. Your V that you're going to find after solving here. After solving, that is the V you're going to substitute. So that is going to be your V after this is your V that you're going to use in this case. So that is your V squared. That's all for this.